So welcome everyone to today's Quantum Thursday. Today's speaker is Chenxu Liu. He's a postdoctoral researcher at Virginia Tech. In fact, he's in my group jointly with a group of Ed Barnes. And Chenxu received his bachelor's in physics from Nankai University in China. And then he came to the US where he went to University of Pittsburgh, where he did his PhD. And he worked on theoretical projects studying how to manipulate photons in physical systems with a focus on quantum computing. Specifically, he worked on superconducting qubits as well as on V-centers in the groups of David Pecker and Gurudev Dutt. And his current research is quite broad. He works on designing robust quantum communication protocols for various physical systems, as well as quantum simulation algorithms, with a special focus on superconducting qubits, which is a thread he is continuing in his postdoc. Okay, so with that, I'll pass it on to Chenxu. Oh, okay. I should also say that after his technical part of the talk, we will take questions about the technical part. So yeah, with that, please, Chenxu, go ahead.
Okay, thanks, Sophia, for the introduction, and hello, everyone. My name is Chenxu Liu. So I'm a postdoc at Professor Edwin Barnes and Sophia Economist Group at Virginia Tech right now. So today it's a great pleasure for me to be able to have this chance to present some of my work at Virginia Tech on this C2QA Quantum Thursday event. So today I'm going to talk about the robust generation of photonic graph state for quantum information processing. So, so let me get to the next page. Okay, so so this is an outline for my talk today. So in today's talk, I will at first motivate our work and introduce the graph states, and especially I will talk about how they are very useful in quantum computing and quantum information processing. I will also mention how they can be used for robust quantum communication. So then I will focus on our schemes to generate microwave photonic graph state from superconducting qubit. Specifically, we will focus on two types of graph state. One is the microwave 2D cluster state, and the other one is the photonic repeater graph state. Then I will give a summary of my project, and I will use my like final 10 to 15 minutes to introduce my career path. So yeah, so in recent years, quantum mechanics and related quantum techniques has a very fast proceeding, especially in like applications and building quantum computers. There are many very awesome works about using like physical platforms to achieve very useful quantum computing tasks. These physical systems, for example, like the superconducting qubit systems and the trapped ion system, trapped neutral atom system, and the quantum dot system, and also the photonic system. So these are all very promising candidates for quantum computings and quantum information processing. However, to build a large-scale quantum computer in the future, we may face, for example, the scalability problems. One aspect of the problem is like, for example, in the trapped ion systems, a Paul trap that holds that can hold about hundreds of trapped ions, which is probably not enough for a very large quantum computing task. And similar for the superconducting qubit system, one chip can have about hundreds of transmon qubit built on a same chip, but it's hard to imagine that there are like millions of different transmon qubits that integrated inside a single like giant superconducting chip. So one possible answer to this problem might be building distributed quantum computing systems instead. So in the distributed quantum computing systems, instead of having a very giant quantum computing chip that can hold like all the qubits are needed for building a real quantum computer, there are multiple quantum computing chips that are involved in the same computation task. So these different chips have a relatively small number of qubits built on them, and they can work collaboratively to finish a single computation task. So one of the key problems to build such kind of a distributed quantum computing system is how to build robust and fast quantum communications between these different chips. Further, this robust quantum communication is also very important for building the quantum networks and quantum internet in the future. So for example, to build a quantum network that entangle different physical systems together, we can take benefit from like taking advantage of different physical quantum platforms. For example, we can use like superconducting qubit system to perform very fast gate operations, and then we can transduce the quantum information from the superconducting qubit system to the photonic systems, for which is good for long-range quantum communications. So the robust quantum information transaction is also very essential to build a quantum network for different physical platforms. And the quantum communication here is also a key problem to solve. So in my following slides, we will see that the photonic graph states are also very useful for achieving the robust quantum communication between these different physical platforms. But before I go into that, I will pause a little bit and introduce you about what is a graph state. So a graph, which is a mathematical concept, consists of a set of vertices and a set of edges. So pictorially, a graph can be represented like this. But the graph state, however, is a pure quantum state. To construct a graph state corresponding to some graph, we can follow in the two following steps. The first step is that for the vertices inside the graph, we can prepare the qubits in the plus state, which is the +1 eigenstate for the Pauli operator. And then for the second step, for the different edges inside the graph that connect to different vertices, we can apply CZ gate between the corresponding qubits. Then we can follow these two steps and write down what is the state corresponding to this graph, which is the graph state. So here I showed an example of this, the state of this this graph state corresponding to this graph, and it's easy. It should be easy for you to just go through these two steps and convince yourself that this is actually the state. So the cluster state is a special type of graph state. Inside the cluster state, the qubits can form a regular lattice. So depending on the dimensionality of the lattice, so there can be one-dimensional cluster state, two-dimensional, and three-dimensional cluster states. So the graph states and also the cluster state are highly entangled state, and they have a wide application in different quantum computing and quantum information processing tasks. So one of the application is in the measurement-based quantum computing. So especially for the two-dimensional, higher dimensional cluster state. So in this measurement-based quantum computing scheme, unlike the gate-based methods where the quantum computing is driven by like the applying quantum gates. So in the measurement-based quantum computing schemes, the quantum computing is driven by the measurements on the qubits. So however, the state before we take any measurements should be an entangled state. And this state is called the resource state for the measurement-based quantum computing. So for example, here we show how we do arbitrary rotation on a single qubit states. This arbitrary rotation can be applied in such a way. So at first we have a single qubit which prepare in the input state, which one which is the one that we want to apply this single qubit rotation. And we apply a CZ to connect this input qubits into the prepared 1D cluster state. And then we take the measurement to these 3 qubits, and the remaining qubits, which are not measured in this process, will be in the state which corresponding to this single qubit rotation on the input state. And similarly, here we show how we can perform a CNOT gate operation on like 2 qubit states. So similarly we apply CZ gate to connect the input qubits with the prepared 2D cluster state and measure the rest of the qubits in according to this measurement pattern, and then the remaining 2 qubits will be in the state which corresponding to the results. So so in these 2 seminal papers, the 2001-2003 paper from the Rusendorf and Bergil, and they show that the 2D and higher dimensional cluster state are proven to be like a universal resource state for measurement-based quantum computing. So, so which means the universal quantum computing can be achieved using these resource states. So the second important application for graph states is to helps to build very robust quantum communications. So suppose that Alice and Bob are separating by a very long distance, and Alice wants to send some quantum information to Bob. So what she can do is that she can prepare, for example, an entangled pair called Bell state, and then she can send 1 qubit out of this pair physically to Bob. But however, because we have a long distance separating them, the loss and decoherence, both of this error will scale exponentially as the distance increases. So the way to solve this problem is introducing quantum repeaters. So with the help of this quantum repeaters, we can separate this long distance between Alice and Bob to some smaller segments. Then these middle quantum repeaters have a very long-lasting quantum system where we can at first construct a quantum entanglement across the small segments, for example, from Alice to the first quantum repeater, and between the first quantum repeater and the second one, etc. And then we can use the entanglement swapping at the quantum repeater to gradually generate longer like entanglement across longer distance. And finally, we can construct a quantum entanglement between Alice and Bob. So in 2015, the author of this Nature Communication paper shows that if we use this this photonic graph states, which is called the all-photonic quantum repeater states, these states can be used as quantum repeaters in this quantum communication task. So this state consists of like 6 like an inner photon qubits layer, which are highly connected, and it also has like 6 outer photon arms, which can be used. So this state can be used as quantum repeaters in this quantum communication task. So so suppose in the middle of this communication channel from Alice to Bob, so there are several nodes which can generate this photonic quantum repeater states. So when this state is produced, we can send left arms to the left and right arm to the right. So in the middle of 2 generation nodes, we can perform Bell measurements on this this outer arm photon qubits, one from left like repeater graph state, and one for the right. So the key point is that we don't need to have all the Bell measurements to succeed on one node. So instead, we can just have 1 Bell measurement to succeed. That is enough. As long as there is one Bell measurement succeed, the quantum entanglement from Alice and Bob can be constructed, and they can use this entanglement to transfer quantum informations. So also more complex repeater graph states with more arms and encoding of the photon qubits can be used to achieve even more robust quantum communications. But so we see that the photonic graph state has a lot of useful implementations or applications in quantum information and quantum computing tasks. So next question is, how are we going to generate this photonic graph state? So this seems to be not a it's not a trivial question. So next, I will move on to introduce you our work. Especially, we will switch from optical photonic system to the microwave photonic system and consider how to generate this graph state using superconducting qubit systems. So as I introduced in my previous slides, the superconducting circuit system is one of the most promising platforms for robust quantum computing and quantum information processing. So the most important element of the superconducting circuit system is the Josephson junction. So here I showed a sketch of the circuit diagram of a transmon qubit. So the transmon, so inside this transmon qubit, the Josephson junction here provide the essential nonlinearity, which makes it not an LC resonator, but an anharmonic LC resonator. So because of this anharmonicity, the transmon qubit becomes a qubit, which means we can selectively drive the lower two levels. So in recent years, more and more qubits are integrated together. However, the robust quantum communications between different chips is still a very essential step to build, for example, a distributed superconducting quantum computers. So in recent years, there are many nice work on this direction, especially at least a few very nice works pursuing this robust quantum communication between different superconducting chips. So the quantum communications between these different chips either relies on using a common transmission line mode as a bus mode to mediate the interaction between the transmon qubit on different chips, or they use a single microwave photon emission and absorption process to achieve a one-way quantum communication between different chips. But how to build a very robust quantum communication, especially if we want to build a quantum communication channel against the photon loss error, this is still a very challenging task. So we think encoding the quantum information into microwave graph states is one of the options. So so besides that, the microwave graph state is also very helpful for transduction the quantum information between different quantum systems. So it is very important to generate this microwave photonic graph states for this quantum communication tasks. So in 2020, Professor Woroff and Ashler have this very nice paper in which they experimentally demonstrate how to deterministically generate the microwave photonic qubits using these two transmon qubits. So specifically, they show how to generate a 1D cluster state of microwave photons. So this generation scheme, especially the generation scheme for the 1D cluster state, is based on this 2009 linear Rudolph proposal, which they use a quantum dot as a photon emitter and work in the optical regime. So in this 2009 linear Rudolph proposal, they propose to use a single quantum emitter, which has this level diagram to generate a 1D cluster state of optical photons. So notice that with this level structure, when the photon emitter is prepared in this plus state, when this photon emitter is pumped, and generate a single photon pulse. And this generated photon qubits, the state of this generated photon qubits is entangled with the state of the photon emitter. So in this way. So then if we apply another Hadamard gate on the photon emitter, we can generate a 2-qubit cluster state of the generated photon and the photon emitter. And if we repeat this process, like pump and let the photon emitter to generate a new photon qubits, and then apply another Hadamard gate on the photon emitter, so we add a new entangled photon in this 1D cluster state of both photons and photon emitter. So then finally, if we have a long enough 1D cluster state, we can measure the quantum the photon emitter along the z-axis and to disentangle it from the rest of the photonic cluster state. So the key part is that so this generation scheme, especially the photon generation from the quantum emitter, can be viewed as this C0 operation between the emitter and the generated photon if we virtually prepare this photon qubit in the 0 state before it's generated. So in this Professor Woroff and Eichler's paper, they like decompose this photon emission process into 2 steps. The first step is to apply a C0 gate between the auxiliary qubits and the emitter qubits. And the second step is to have this emitter qubits to generate a microwave photon into the connected transmission line. And this emission process can be viewed as a the swap operation. So, however, the 1D cluster state is not enough. It is not a universal resource for measurement-based quantum computing. Besides that, the robust quantum communication using microwave photons also requires to generate more like complicated graph states. For example, the photonic quantum repeater state. So in the following of my talk, I'm going to focus on these more complicated microwave graph states. So in the rest of my talk, I'm trying to mainly address the following following questions. So one is that, so how can we generate this like 2D cluster state of microwave photons and more complicated graph states using superconducting qubits, for example, this repeater graph states. And the second question is what are the optimum generation scheme to generate these microwave graph states? Specifically, we consider at a fixed frequency transpond qubit or tunable frequency transpond qubit are more suitable to be used as quantum emitters. The second is that which type of photonic qubit encoding method we can use for better microwave states. So the third question is, what are the main challenges when we want to produce large microwave graph states, and if we can like remove or mitigate it? So to construct the generation circuit with transpond qubits, we have 2 types of transmonds. So how are they like different from one with each other? So for fixed frequency transpond qubit, so as they suffer less phase noise, they usually have longer coherence time, which makes their gate operations usually to have higher fidelities. However, the gate operation time is usually longer. So this means in the generation scheme, when we need to apply some gates between some qubits, some idling qubits needs to wait for longer time, which may generate more decay and decoherence error on the transpond qubits, which may be bad for the generated state fidelity. But compared to the fixed frequency transpond qubit, the tunable frequency transpond qubit is kind of in the opposite direction. So they can have very fast gate operations, but usually they will have shorter coherence time compared to the fixed ones. So in order to see which one is better, we will, in my later of my slides, we will move on to see to work in with different superconducting qubit systems to generate different types of microwave photonic graph states and see which one is better. And further, we also want to see what are the best encoding method for different microwave photonic qubits. So here, one of the most straightforward encoding method is to use the Folk basis encoding. So where the quantum informations in the Folk basis encoding photon qubits is encoded into presence or absence of a single photon pulse in propagating inside, for example, the transmission line. So this is also the encoding method adopted in Professor Worath and Ashler's paper. But this method, so basically this method only uses a single photon emission window to to encode the quantum information. So so in that sense, we can keep the generation time of this of a single Folk basis encoded photon to be short, such that we can keep the decay and decoherence error on the transmon qubits minimum. So which will give the best state fidelity of the microwave graph states. However, the single qubit, so if we want to apply single qubit gate operations on the Folk basis encoded microwave photon, so usually this single qubit gate operations rely on like release and cache methods. This single qubit gate operations does not have a very high gate fidelity with the current experimental setups. So the second encoding method we are going to consider is the two-rail encoding methods. So this encoding methods rely on using two spatial modes where the quantum information is encoded into the photon pulses in either of the spatial modes. So this encoding methods allows an easier way to perform single qubit gate operations, just like in the optical photonic systems. So in the microwave photonic systems, we can use the microwave photonic device, which just like a beam splitter in the optical regime to perform single qubit gates on these two-rail encoding qubits. So however, as we need to map a single bit of quantum information into two different modes, which essentially needs two photon emission windows, this will make the generation procedure is like generate the time that's spent to generate a single bit of two-rail encoded photon relatively long, and so the which will give like more decay and decoherence error while the transmon qubits are waiting. So to answer which type of transmon qubits and which type of like photonic qubits, photonic qubit encoding method is better, we specifically focus on the generation scheme of the following two microwave graph states: the 2D cluster state of microwave photons and the repeater graph states for microwave photons. So we start from the 2D cluster state of microwave photons. So following the linear Rudolph proposal in 2009, in the optical regime, the 2D cluster state of optical photons can be generated by a 1D chain of quantum emitters, which have the similar electronic structures. So, so similar to the 1D generation schemes, the photon emission and the following Hadamard gates on the quantum emitters will generate a new column of entangled photon into this 2D cluster state. But the essential step is that between the two photon generation step, we need to apply the CZ gate between the quantum emitters, such that we can generate this vertical edges in the 2D cluster state of the optical photons. So notice that there is no need to apply a single qubit gates on the generated photon pulse. So in the corresponding in our microwave proposal, so we propose to use the folk basis encoding methods to maximize the generated state fidelity. So, so here is our proposed generation circuit for superconducting qubits. So we consider using multiple photon generation units, which consists of these two transmon qubits, one as the auxiliary qubits and the other one as the emitter qubits. In order to apply the CZ gate between different photon generation units, we couple the auxiliary qubits in different this photon generation unit together, such that we can apply this CZ gate. So in order to generate a high fidelity 2D microwave cluster state, we not only need to have very high fidelity gate operations between transmon qubits, we also want the emitter to have faster photon emission process. But these two requirements seems to be a little bit contradictory, because if we want faster photon emission process from the emitter to the coupled transmission line, so we need to have smaller T1 time for the emitter qubits. But that will also decrease the state fidelity, the gate fidelity between, for example, auxiliary qubits and the emitter qubit. So in order to solve this problem, we propose to use a tunable coupler to couple the emitter and the transmission line, such that so when we want to have a very fast photon emission from the emitter, we can turn this coupling on to have a strong coupling between the emitter and the transmission line. And when we want to apply gate operations between auxiliary qubits and the emitter qubits, we can turn this off to remain a high fidelity gate operations between the different qubits. So similar to the optical proposal, we can use this generator circuit to generate a 2D cluster state of microwave photons. But the generated photon qubits are connected to the auxiliary qubits instead. So the emitter qubits will be disentangled with the rest of the qubits. So for a general case, when we want to generate a 2D cluster state with capital M, total M photon qubits, and using like K photon generation units, the fidelity of the generated 2D cluster state using either fixed frequency transmon qubit and tunable frequency transmon qubit can be estimated using these two equations. So note that the cross-resonant gate and the CZ gate are the native gate set for the fixed frequency transmon qubit and the tunable frequency transmon qubits. So we translate the required 2-qubit gates in order to generate this 2D cluster state using either cross-resonant gates or the CZ gates. So in order to have a more intuitive feeling about which one is better, so we consider a special case where there are only two photon generation units. Then we can generate a 2/n photonic 2D cluster state for microwave photons. So we calculate what is the maximum photon number inside this generated 2D cluster state generated by either fixed frequency or tunable frequency transmon qubit. And so we require the generated states has a minimum fidelity 0.8, and we tune the photon generation window, which will control how much decay and decoherence error on the transmon qubits while it is waiting for the photon emission. And also we tune the infidelity of the CNOT operation for fixed frequency transmon qubit and the CZ operation for the tunable frequency transmon qubit. So in both cases, we can generate about 16 photon qubits, but still have a very relatively high state fidelity, like 0.8, for both of the transmon qubit systems. So so these two types of transmon qubit does not show much like difference in this parametric space we are chosen. So the second example of the microwave graph state we are considering to generate is the repeater graph states. So in 2017, this PRX paper, also from our group, proposed a scheme to generate this repeater graph state for optical photons using one photon emitter and another matter qubits, which serve as an anchor qubit. So here I sketch what is the generation scheme proposed in this PRX paper. In this generation scheme, at first we apply a CZ gate to entangle the anchor qubit and the emitter qubits. Then we pump the emitter qubits twice to generate 2 more photon qubits. And then we apply Hadamard gate on the photon qubits to make the 4 qubits in this graph state. And after that, we can measure the emitter qubit in the X basis and to transfer the generated photon qubits to the anchor qubits. So in that way, we can generate 1 photon arms in this tree-like graph states. So we can repeat this process by another time. Then we can generate a second photon arm in this tree-like graph states. So when we repeat this process 6 times, and all 6 photon arms are generated and rooted at this anchor qubit, we can perform a poly-Y measurement on the anchor qubits and finalize the generation process for this photonic quantum repeater state. So in order to generate this repeater graph state for microwave photons, we propose to use another transpond qubits, which serve as the anchor qubits in our generation scheme. And this anchor qubit will couples to the auxiliary qubits in the photon generation units, such that we can apply the entangling gates like the CZ gate between them. So because in the optical generation scheme, we noticed that the photon qubits, we need to apply single qubit gates on the photon qubits. So we choose to use the 2-rail encoding method for the generated photon qubits. In that sense, we can have an easier way and high fidelity like single qubit gate operations on the generated microwave photonic qubits. So as the microwave photon emission window is usually much longer than the 2-qubit gate time between the transpond qubits. So in order to speed up the photon generation process, we propose to use a second transpond qubit that serves as an additional emitter to speed up the photon qubit generation scheme. But if we just follow the quantum dot protocol where the 6 photon branches are generated sequentially, the decay and decoherence error on this anchor qubit will dominates. To get a better graph states, we need to reduce the error coming from this anchor qubits while it's like waiting for all the 6 branches are generated. So we noticed that in this repeater graph state generation scheme, we can use the parallelization to reduce this decay and decoherence error coming from the anchor qubit. So specifically, instead of using a single photon generation unit to generate this different photon arms sequentially, we can use 6 photon generation units and let them generate the photon branches simultaneously. After all the photon branches are generated, we can apply the CZ gate between the anchor qubit and the auxiliary qubits in different photon generation units. And after that, we can simultaneously measure the auxiliary qubits inside different photon generation units to disentangle it and transfer the generated photon qubits to the anchor qubit to finalize this tree-like state preparation, and then do the Y measurement on the anchor qubits to finalize the generation scheme. So with this parallelization methods, we consider what is the fidelity of this microwave 6-branch tree-like graph state by either the fixed frequency or the tunable frequency transmon qubit. So here we plot what is the overall state fidelity for both the fixed frequency transmon qubit and the tunable frequency transmon qubit. So both of the system can generate the state with good fidelities. So for fixed frequency transmon qubit, we see that the fidelity is slightly better than the tunable frequency transmon qubit. So now I will summarize my first part of my talk. So we provide the circuit design for generating like the 2D microwave cluster state and this tree-like graph state, and correspondingly the photonic quantum repeater state. And we also show that the generated states can have, especially for the microwave 2D cluster state and the repeater graph state, can be generated with a pretty good state fidelity. And we also design the single qubit gate schemes for microwave photon qubits and estimate what is the gate fidelity. So that will be found in the manuscript we're preparing, and hopefully you will see that within within a few weeks. We also investigating to use other type of superconducting qubits and photonic qubits, and also combine with error correction codes to improve the performance of the microwave graph state generation. Yeah, that is all I want to say about my projects. And thank you for your attention. I want to pause here a little bit to see if there's any questions. Oh, seems I haven't seen any question in the chat. So
yes, you can go ahead with the second part then, and if people have questions, they can ask them at the end.
Okay, so probably I will just move on to my second part to talk about my career path, and hopefully, so yeah, so I'm the questions will come in the chat, and we'll try to like answer those questions after my second part. So yeah, so let me see. Yeah, so so then I will briefly introduce you my like career path, and so my subtitle for this part is like from Pitt to Virginia Tech, and from experiment to theory. So before I joined the PhD program at University of Pittsburgh, when I was in my undergrad period in China, so I'm more working with the experimental groups, especially focusing on experimental optical physics. So in my undergrad period, so we are working more with, for example, the light propagating inside the fibers, and we try to couple the light with some materials, for example, like graphenes, to try to introduce stronger nonlinearity, which can control the light propagating inside the like optical systems. So it is around the same time I when I learned more advanced quantum mechanics and start learning quantum optics. I know a lot of fascinating like phenomena, especially in quantum optics. So I got kind of attracted by those interesting ideas and interesting like theory. So then I decided to like join University of Pittsburgh for the PhD program, following Professor Gurudev Dutt. So Professor Gurudev Dutt has a very good experimental group in University of Pittsburgh. So in Gurudev's group, so we are focusing on a physical system called nitrogen vacancy centers. So the nitrogen vacancy center, just in case you don't familiar with that, the nitrogen vacancy centers or NV centers is a type of defects in the diamond. And so the reason why this NV center is very interesting and popular is because the ground state spin level for the NV centers has a very long coherence time. So it is a very promising candidates for like quantum computing and quantum information task. So so we noticed that on like 2015, the researchers at Delft, they demonstrate experimentally that they can use like Herodian methods to entangle two far separated NV centers in their lab. So I think in this work, they the distance between the two NV centers is like 1.4 kilometers. So so then we start thinking whether we can do something similar and more interesting, like can we perform a single qubit gates, like Herodian single qubit gates, rather than just entangle the two qubits together. So that is one of the projects I worked with Professor Gurdov Dutt, and also with Professor David Packer, who is a theorist in at University of Pittsburgh. So so at first we start designing the experiments and trying to find a way to get this Herodian gate scheme. So then we after our research, we propose a way to use two NV centers embedded in diamond waveguide and pumped by like selected CW pumping laser to drive these two NV centers. And we have two detectors on both sides of the diamond waveguide, and to receive this single photon clip, like single photon like detection process. So when the so Herodian on this single photon detection, we can perform a gate operation on these two NV centers. So I will not go very deep into this project, but we have a paper on PRA. So if you're interested, you can go and find it. So so it's around the same time I start to see how like so what is the life about, like what is the life about if you are working as a theorist. So because for this work we are mainly focused on working on like proposing the experiment and understanding what is the electronic structure of the NV centers and how we like drive the NV centers and calculating what is the like the transition rate, etc. At the meantime, I'm a little bit like kind of annoyed by like waiting in the queue to be trained to use those very large like facilities, like for example EBL or FBI to do this experiment. So I talked with Professor David Packer and say, can I just switch from experiment to theory? And David said, yeah, sure. Well, I have to say David is a very nice guy, and I know some of the like the theory advisors have a very high standard for their students. So David told me that since you have a strong background for experiments, why not we work in like the intermediate region where we still work in the theory side, but we work closely with experimental people to see if we can design some interesting experiment for them. So at the similar around the same time, Professor Michael Hadrich joined University of Pittsburgh and started his very good group at University of Pittsburgh working on superconducting circuit systems. So around the same time, I'm kind of very interested in this superconducting qubit system, and we know that there's a lot of things to understand and discover using like in the circuit QED system. So we start talk with Michael, and we start by understanding like the performance or understanding the physics in their one of their device they are using, which is called Josephson parametric amplifiers. So I have to say there are different types of Josephson parametric amplifiers. So we are focusing on one type of the Josephson parametric amplifier, which is called the Josephson ring modulator based Josephson parametric amplifier. So we try to construct the dynamics, like the equation of motion to describe the Josephson parametric amplifier and understand what is the dynamic range of the of this amplifier and how are we going to optimize the performance of this parametric amplifier. So we based on our analysis, we also like closely talk with the students in Michael's lab, and we are designing like new parametric amplifier and which has better performance. So then we think it a little bit further. So we noticed that the Josephson junction provides a very strong nonlinearity in the microwave regime. So we think whether we can use this strong nonlinearity to do something more fancy or like to see more interesting physics out of the normal quantum optics devices. For example, one of the devices we are considering is a laser. So inside the laser system, so we have the pumping media, which will be pumped and interact with the cavity field and build up the population inside the cavity field. And the cavity field will talk with the output field, which will generate this strong laser beam going out from the laser cavity. So in the standard laser theory, we think that the atom and the cavity field are linearly coupled, which means this coupling always be modeled by a James Cumming type of coupling. And similarly, from the cavity to the outside bath, this cavity bath coupling is also linear. So similarly, we can build this conventional laser on chip using superconducting qubit systems. Like we can have like transmon qubits. By the way, we use Snell qubits to achieve the incoherent driving from the ground state to the first excited state of the transmon qubit. And the microwave cavity, which is served as this laser cavity, is modeled by this LC resonator. And these three different segments are also linearly coupled through the capacitor, for example. And this can give us a laser in the microwave regime using superconducting qubit systems. But we are thinking if we can do something more. So at around the same time, we found an old paper, which is from 1999 by Professor Weissman. And in this paper, he talks about using a different like cavity operator, which is this E operator, or in other words, the Susskind-Golgover operator. To use this E operator to replace the normal like lowering and raising operator for the cavity field A, then we can see some interesting phenomena where if we use this coupling Hamiltonian between the atom and the cavity, the laser line width can be suppressed by a half beyond the standard limit of the line width of the laser. So we are thinking if we can build such a E operator in using like a superconducting circuit system, and further, if we can use this E operator to couple the cavity and the bus. In other words, we try to do some bus engineering to further suppress the line width of the laser. So then we came up with this nonlinear circuits and provide a cavity operator, which I call it capital A here. So if we see the first off-diagonal elements of this A operator, it has a like plateau, a flat plateau region, where if we tune our device working in this region, the line width of this this device, the laser, can be further suppressed from the standard quantum limit, which shown by this this green line. So then we so after our collaboration, so we finished this theory work and hand this plan to Professor Michael Hedges' group, and they are trying to they are trying to like implement this laser devices. And then I moved to, after my graduation, I moved to Virginia Tech, and now I'm working with Professor Sofia Ikamu and Professor Edwin Barnes, and now we have a strong theory group here at Virginia Tech. And for me, I'm currently working on like robust quantum communication protocols for different physical systems, for example, the like using superconducting qubit systems. And also we are considering using Niscale quantum computing platforms to do some useful quantum simulations and trying to understand more like how to use the quantum computer to do very interesting computation tasks. And yeah, that is all I want to share for my career path, and I'm happy to take any questions.
Okay, great. Thank you, Chenxu. Actually, there are a few questions. So there are some technical ones. I'll go through those first. So one is by Kevin Smith. At the end of your talk, you showed some results for generating graph states where you use 6 anchors and parallelize the CZ gates and measurements. Could you clarify what is limiting the fidelity in the plots you showed after this?
Oh, so actually, so here I have to say one, so just one words to a little bit correction. So here in this parallelization methods, we're not using 6 anchor. So we are using like 6 generation units, but a single anchor. So go back to the question. So what limits these the fidelity of this generated state? So we also perform the calculation to estimate that. So basically what we do is we try to remove some of the imperfections in this generation scheme. For example, if we set the 2 qubit gates to be perfect, what is the resulting state fidelity is, and etc. So we found that the main error is coming from the 2 qubit gates right now. So in order to get a better like state fidelity, we need to optimize the 2 qubit gates. Yeah,
great.
so,
the next question is by Ted Yoder, and that asks, you mentioned when introducing repeater states that only one of the 3 Bell measurements needs to succeed. What does it mean to succeed in this context, and what is the probability of success?
Okay, so so let me get back to that slide. It's a little bit long. So I think basically so basically if we think about the Bell measurements in the optical regimes, so because here the Bell measurement is like a parity projection on the 2 incoming photons. In optical regime, that success probability is just like 1/2. So that means there is a half of the chance you will get a succeed, and half of the chance you will get you will not succeed. Which means maybe 2 photons go into the same detection path, or maybe you miss the basically if we ignore the photon loss, then basically it's like there half of the chance the 2 incoming photon will get into the same path, and that is considered to be a failure. But when the Bell measurements succeed, what we have is like we have a polarized beam splitter to so basically we send in this, for example, these 2 photons through a polarized beam splitter and have 2 detectors on the 2 output path. And when both of the detector clicks, we know there is this Bell measurement succeed, and this probability is like 1/2. And when this Bell measurement succeed, and these 2 qubits will get entangled. So.
Great. Yeah, I think that answered it. I want to move on because there's a few more questions. So I'm going to exhaust the technical questions first, and then I'll ask you one more. Yeah. So Kevin Smith asks, the E operators you mentioned, I think this was near the end of your talk about your Nature Communications paper.
Okay.
Is it just missing? I don't think you need to go all the way there. Maybe you can answer without flipping through.
Okay.
Is it just missing the square root of n? And can you clarify what this changes in intuitive terms? So I think the question is comparing to the AA dagger, is the only difference the square root n?
So I think the problem, that is a good question actually. So I have to state that in my talk. So basically starting from the normal A operators, you will see that there is a square root of n, right? That is the bosonic amplification factor. So especially if we want to get rid of the boson amplification factor, we need to have higher order nonlinearities, right? So so in that sense, yes. So basically, we want to suppress the boson amplification in the photonic system and try to get that E operator. And one of the reason, which is not very rigorous, to say why that E operator can suppress the noise, especially the phase noise, is that the E operator is kind of the eigen operator for the phase. So that is a very hand-wavy explanation. There is a lot of discussion on how to define the quantum phase as an operator, but you can think of that way. So that is why there is no added noise into the system. So am I answer the question? So
yes. So I think there's one last question, which is more about the second part of your talk, the more kind of career. And it's, what are the next steps in your research in relation to your personal goals?
Sorry, could you repeat the question?
Sure. What are the next steps in your research in relation to your personal goals? So I think this is more about where you kind of think of going in the future, career-wise. That's my understanding of the question.
Yeah, that's a hard question, and it's a really long future goal, right? So my understanding is, so my thinking right now is so here at Virginia Tech, we have a really strong group about understanding how to perform robust quantum communication, and how are we going to do robust quantum quantum simulation using the current quantum computers. So I think that is a good start. So I think in my future, I'm trying to build a more solid background, especially in the quantum computing, quantum information processing, this research field. And I think the quantum computing is one of the very promising direction in the future, especially in the near future, maybe 50 years. So maybe 50 years, we can build a real quantum computer. We can really do something fascinating from using that. So I hope within my career, I can contribute myself into the research and trying to move our this whole society by a little bit. So try my best. So yeah.
Great.
So,
yeah, thank you, Chenxu. Thank you everyone for the questions and for attending. And we will have, the next Quantum Thursdays, I believe, is Leila Hormozi from Brookhaven. So with that, let's conclude today's talk, and thank you again very much.
Okay, thank you for joining.